Welcome to another deep dive, and today we're going to be looking at a really cool book, Pattern Recognition and Machine Learning by Christopher M. Bishop. Um, Basically, it's all about how we can teach computers to, see patterns and make predictions, almost like you're building a little mini Skynet, but for good.
Well, it's funny you should mention that because Bishop actually goes beyond just the algorithms. He really emphasizes that foundation of math, so probability theory and Bayesian methods and even decision theory, the stuff that really makes those algorithms work.
So it's more than just plugging in code. You have to understand the concepts behind it.
Yeah, it's like the difference between just following a recipe and actually understanding the chemistry of baking. You can bake a decent cake by just following instructions, but if you know why each ingredient is there, you can improvise. You could even create something new.
I like that. Okay, so Bishop gives us these foundations, and then what does he do with that? Does he walk us through any specific types of machine learning? I know everyone always talks about neural networks.
Yeah, he does. He covers a huge range from simple linear models to, like you said, complex neural networks and even things like kernel methods. It's almost like he's giving you a toolbox. So each tool is designed for a different kind of pattern recognition problem.
Now, something else that caught my eye, he talks about this cursive dimensionality. That sounds kind of scary. Is it as bad as it sounds?
It can be. You can imagine you're trying to find one specific grain of sand on a beach. Kind of tough, right? But now imagine trying to find that same grain of sand, but the beach is spread across the entire Earth.
Oh, wow.
That's kind of what happens with data in high dimensions. Our normal ways of finding patterns just don't really work as well.
So more data isn't always better. Huh. That's counterintuitive. So what's the solution? Do we just ignore high-dimensional data?
Not necessarily. There are ways to handle it. So sometimes you can reduce the number of dimensions, kind of like compressing a file. Or we can use special algorithms that can work in those vast high-dimensional spaces.
Let's go back to that foundation for a second. So Bishop starts with the basics, right? What are some of the core ideas that he lays out?
Well, he dives into probability and curve fitting. Basically, it's all about finding the best mathematical representation for your data. And he even introduces specific notations like X to represent expectation, so that's the average value we expect to see, or convex for covariance, which tells us how two variables kind of change together.
So it's like finding the line of best fit, but much more advanced.
Exactly. He uses a really good example of fitting a polynomial curve to your data points. It's like connecting the dots, but instead of drawing straight lines between them, you're trying to find the smoothest curve that goes through all those points or near them. And you can actually measure how well the curve fits using something called the root mean square error, or RMS error for short.
I see. Okay, so we're getting into some of the details here. But isn't there a risk that we could make a model that fits perfectly to the data we already have, but then it fails when we try to use it on new data?
Yeah, that's called overfitting. That's a big one. You can think of it like a student who just memorizes all the answers for a test instead of actually understanding the material. They might ace that one test, but they're not going to be able to apply it to anything new.
So how do we avoid overfitting? How do we avoid creating a model that's just memorizing the data?
Well, that's where Bayesian methods come in. They're pretty cool because instead of just finding the best fit for the data you have right now, they force you to consider things like prior knowledge and even uncertainty. This helps you build models that generalize better so they can handle new data.
So it's almost like we're adding a dose of common sense into our machine learning.
Yeah, exactly. Like you're saying to your model, hey, don't just blindly fit this data. Think about what we already know about the world and, be ready for some surprises.
This is already pretty mind-blowing, and I feel like we've only just scratched the surface. So what else does Bishop have in store for us in this deep dive into building intelligent machines?
Well, he dives into something called decision theory, which is all about making the best choices when you're faced with uncertainty. Think of it as a framework for weighing the potential costs and benefits of different actions.
Oh, so like a risk versus reward calculation, but with more math involved.
Exactly. And he introduces something called a loss function to actually quantify the cost of making the wrong decision. And that helps you prioritize the most important decisions in your machine learning models. Like, for example, he uses a great illustration of a loss matrix for diagnosing cancer. If you misclassify a patient who actually has cancer as healthy, that's a much higher cost than misclassifying a healthy patient as having cancer.
Yeah, that makes a lot of sense. But how do we even measure the uncertainty in our data in the first place?
Well, that's where this whole field of information theory comes in. It's really cool because it gives us these tools to quantify things like entropy. Entropy is basically a measure of uncertainty in like a probability distribution.
Okay.
So you can imagine like flipping a coin. There's a lot of entropy there because the outcome is, uncertain. But if you had a rigged coin that always landed on heads, well, there's zero entropy because you already know for sure what's going to happen.
So the less certain we are, the higher the entropy. I'm seeing how this ties into machine learning now.
Yeah, exactly. Understanding entropy and all these other information theory concepts helps us design better algorithms that can actually deal with the uncertainty in our data. Another important concept is the Kullback-Leibler divergence, which basically measures how different two probability distributions are from each other. It's kind of like a distance metric, but for probability distributions.
We're getting pretty deep into the weeds here. I'm really seeing the value of understanding these concepts. I can't believe how much we've already covered, and we haven't even gotten to the algorithms yet.
Yeah, we've laid a really good foundation, but there's so much more to explore. What's great about Bishop is he doesn't just throw algorithms at you, he gives you the tools to understand why and how they work. So remember that cursive dimensionality we were talking about earlier? Well, to really understand why it's such a challenge, we need to talk about Gaussian distributions. They're kind of like the bread and butter of a lot of machine learning techniques.
Yeah, okay, back to the curse. So more dimensions basically make the data harder to work with, right? Like searching for a needle in an ever-expanding haystack. How do these Gaussian distributions fit into all of this?
Well, think of a bell curve, right? That's the shape of a Gaussian distribution. It's like everywhere in statistics. And Bishop shows us how to use these curves to model data, especially when you have multiple features, each represented by a different dimension.
So instead of like a single bell curve, we're dealing with like multi-dimensional bell curves. My brain's starting to hurt a little.
Yeah, it's a lot to visualize for sure. But the main point is that in higher dimensions, the volume of the space grows like exponentially. Imagine a balloon. As you blow more air into it, the space inside expands rapidly. And the same thing happens with data as you add more dimensions.
So the data points are like spread out much farther apart, and that makes it tougher to find meaningful patterns.
Exactly. It's like if you were trying to map out a city, but you only had like a handful of landmarks, and they're scattered across a vast landscape. That concept of closeness or similarity becomes less intuitive in those high-dimensional spaces. And that makes it harder for algorithms to, cluster the data and make accurate predictions.
Okay, I'm starting to get why that cursive dimensionality is such a pain. It's like our intuition about how data behaves just breaks down when you have all these extra dimensions.
Exactly. And that's why Bishop spends quite a bit of time in the book exploring different ways to approach this challenge. One method he covers is called the maximum likelihood approach. And it basically helps us estimate the parameters of our models. Those are the values that define like the shape of those multidimensional bell curves.
So we're basically trying to find the bell curve that fits our data best.
Exactly. It's like finding the right size hat for your head. But remember, just like with curve fitting, there's that danger of overfitting. So we could end up with a model that perfectly fits the data we already have, but then it completely fails when we try to use it on new data.
Oh, so we need that common sense boost again. How do Bayesian methods come in here?
Well, with Bayesian methods, instead of just searching for the maximum likelihood estimate, you can actually incorporate prior knowledge about the parameters. So it's like saying, okay, based on what we already know, we think the hat size should be somewhere between small and medium. So that helps us narrow down the possibilities and avoid overfitting.
I see, I see. Okay, so we've got these casting distributions, and we have ways to estimate their parameters. But what if our data doesn't fit neatly into these bell curve shapes?
That's where these things called non-parametric methods come in. They're really cool because they give you a more flexible approach so you can actually model probability densities directly from the data without making assumptions about what shape it should have.
So instead of trying to force the data into some predefined shape, we're letting the data guide the model.
Yeah, that's a great way to put it. It's like sculpting clay instead of trying to fit square blocks into a round hole.
I like it.
Two key non-parametric methods that Bishop talks about are kernel density estimation and k-nearest neighbors.
Okay, those sound familiar. Can you remind me how those work?
Sure. So in kernel density estimation, you basically smooth out those data points using what's called a kernel function, and that creates this continuous probability density estimate. So you're kind of like taking a bunch of individual data points and blurring them together to get a bigger picture of the distribution.
Okay, makes sense. And what about k-nearest neighbors?
Well, imagine you're trying to classify a new data point. With k-nearest neighbors, what you do is you look at the k closest data points in your training set, and then you assign the new point to whichever class is the majority among its neighbors. It's a pretty simple technique, but it can be surprisingly effective, especially for classification.
I like how those non-parametric methods are so data-driven. They're really adapting to the shape of the data instead of forcing it into a specific mold. But are there any, downsides to using them?
Well, like with anything, there are trade-offs. One thing is they can be computationally expensive, especially if you have really large data sets, and they can also require careful tuning of the parameters, like choosing the right kernel or figuring out the best number of neighbors.
So it's a balancing act. Flexibility versus computational efficiency. Guess there's no free lunch in machine learning, huh?
Not really. But the nice thing is, if you understand the strengths and weaknesses of each approach, you can choose the right tool for the job.
I already feel like I have so many more tools in my machine learning toolbox now. Bishop really lays out a great framework for understanding these complex ideas. But what about the more practical side of things? Like, how do we actually put all of this into practice with real-world problems?
Well, that's one of the things Bishop is really good at, connecting to theory to practice. He spends a lot of time in the book explaining specific algorithms, from the more basic linear models to the really complex stuff like neural networks and support vector machines.
Oh yeah, I'm definitely interested in those algorithms. But first, I just want to say, it's pretty impressive how Bishop can explain all this super complex math in a way that's actually understandable. I was a little intimidated at first, but he really breaks it down step by step.
Yeah, he's really good at making those ideas accessible. He uses clear language, helpful visuals, and great examples. And he also revisits those key concepts throughout the book, so it really helps reinforce your understanding as you go.
It's like having a patient teacher guiding us through this whole world of machine learning. Now that we have a good foundation, I'm excited to see how he ties all this together with those algorithms that are changing the world. Okay, so we've talked about the math, all those concepts, the potential issues. Now let's get to the good stuff, the algorithms. What are some of the big ones, the heavy hitters that Bishop explains?
Well, he covers a whole bunch, starting with, those really fundamental linear models. You can kind of think of them as like the starter kit for machine learning. They're simple, pretty easy to grasp, and they're actually surprisingly effective for a lot of different tasks.
Linear models. Okay, that rings a bell like from way back high school algebra. Is that basically just like finding the equation for a straight line?
Yeah, it's the same basic idea, but instead of just having two variables, we might have, hundreds or even thousands. So you can think of it like trying to predict house prices. You've got all these factors like, size, location, number of bedrooms. A linear model tries to figure out like the best weighted combination of all those features to give you an accurate prediction.
So it's kind of like assigning like a score to each feature based on how important it is.
Exactly. And then you basically combine those scores to come up with your final prediction. Of course, real world data, it's worthily perfectly linear, right? That's where Bishop introduces these more complex algorithms like, perceptrons and neural networks.
Ah, neural networks. Those are like the rock stars of the machine learning world these days. What makes them so special?
Well, they're actually inspired by how the human brain works, with these interconnected nodes that process and send information. And Bishop really dives into how these networks learn from data by adjusting the connections between all those nodes to get better and better at making predictions. It's almost like, training a dog. You reward it for good behavior, and over time, it learns how to do the tricks you want.
So instead of like programming the rules ourselves, we're letting the neural network kind of figure out those patterns on its own?
Exactly. That's what's so powerful about these algorithms. They can actually learn these complex, nonlinear relationships that you just couldn't capture with traditional programming.
It's mind-blowing, but it also sounds super complicated. Does Bishop make it understandable for someone who's not like a math whiz?
Oh, he's really good at breaking it down. He really walks you through the steps of actually building these models and explains like the intuition behind each decision. He doesn't just throw equations at you. He shows you why and how things work so you really understand what's going on under the hood.
Yeah, I don't want to just like blindly use these algorithms. I want to understand how they work and like why they're so good at what they do.
Yeah, and Bishop really gives you the tools to do that. He even talks about all the different types of neural networks because, each one has its own strengths and weaknesses. For example, there are these things called convolutional neural networks, and they're really good at image recognition. And then you've got recurrent neural networks. They're really good at processing data that comes in a sequence, like text or speech.
It's like we have a whole arsenal of machine learning tools. Each one is for a different job.
Exactly. But Bishop also makes it clear that just choosing the right algorithm, that's only one piece of the puzzle. You need to really think about, how you're going to prepare your data, what features you're going to use, how to evaluate the model, all those different steps that go into making a successful machine learning system.
It's definitely more than just picking an algorithm and pressing go.
It really is. It's a whole process, a journey of discovery and trying things out. And Bishop gives you a really good roadmap for that journey to help you navigate all the challenges and the successes along the way.
This deep dive has been amazing. I feel like I have a whole new perspective on machine learning, like how it works and the potential it has.
Yeah, it's a really powerful stuff, and it's already changing so many different fields. And with Bishop's book as a guide, we can all be part of shaping that future.
So for everyone listening out there who's now totally psyched about machine learning, what's the big takeaway, like the thing they should be thinking about as they go out and explore this amazing world?
I think the main thing to remember is that machine learning, it's not magic. It's built on this foundation of math and statistics and really smart algorithms. And by understanding those principles, you can really unlock its true potential and avoid some of those pitfalls of just blindly applying techniques.
That's a great point. And who knows, maybe one of our listeners will be the one to come up with the next big breakthrough in machine learning that changes everything.
Yeah, the possibilities really are endless. Just keep exploring, keep learning, and, keep pushing the boundaries of what's possible with machine learning. CAC are